everyone. Thank you so much for coming to my talk. My name is Allison, and I hope some of you were lured in by the title of this talk, because there was a part of me that had a strange sense of satisfaction bringing a Britney Spears song into a data engineering talk. But I'm actually not really going to talk too much about Britney today. I'm mostly going to be talking about the work that we at Cortico, which is a nonprofit out of the MIT Media Lab, have been doing to identify duplicate content in talk radio. All right, so I'm going to start by going over our problem, why we're even looking at this, then talk about a solution, the existing tools out there, and then go more in depth about our solution, both in an algorithm perspective as well as an infrastructure perspective, because it turns out we needed to throw quite a few machines at this problem. And finally show some hopefully nice looking results. All right, so you might be thinking, wait, talk radio, that's kind of weird that's kind of a weird data source. And as far as we know, we are one of the only places that is automatically ingesting and transcribing talk radio. 163 radio stations across the country, so this is a map of some of the talk radio we've been ingesting. And this is one of our products called Earshot, and it's a product for journalists to surface. The goal is that they can better hear local voices, so what people in certain communities are talking about. So here's an example of what you might use Earshot for. So let's say I want to know what people in Boston are talking about regarding donuts. And not too surprisingly, we get a lot of results for Dunkin' Donuts. And you can so you could click the play button and hear what people are calling in about donuts, if that is what you are interested in. Another thing is, let's say you don't know really what you're interested in, but you just want to get a sense of what people are talking about in Boston. So this screenshot was taken a few weeks ago, October 22nd. And so you can see there was like migrant caravan. There's also this DNA test in Pocahontas. And we can probably see that that's probably a result of Elizabeth Warren releasing the results of her DNA test. And this is a pretty Boston issue, given that Elizabeth Warren is the senator of Massachusetts and continues to be. All right, so then I chose another city, Atlanta, Georgia, mostly because I personally don't know that much about Atlanta, Georgia. So we also see caravan, so that's sort of more of a national news topic. And we also see some new names show up, such as Troy Davis. So I also did not know who that was, so I looked it up. And it turns out it was the 6-year anniversary of a pretty high-profile murder in the Georgia area. So we can start to see that we are now getting more into local issues. But if we take a look at this list again, we start to see some sort of weird things like GoDaddy. I looked it up, and I personally didn't find anything about GoDaddy in the news. There might have been something that I missed, but in my opinion, I think it's more likely that it was just a commercial that aired on talk radio, maybe in a few radio stations in Georgia, and that got picked up by our algorithms and said, yeah, GoDaddy is trending in Atlanta. So we can start to see that duplicates in public radio isn't great. We don't want a user to have to go through multiples of the same thing and hear multiple of the same content, even though it's on different radio stations. And it gets overcounted for in topic detection, as we just saw. And finally, it's harder to hear local voices if there's too much syndicated content, and our whole goal is to hear local voices. All right, so we started to look for a solution. And the things that here are our goals. We wanted to increase our duplicate detection accuracy, obviously. But also, we are one of the only places, as far as we know, that is even looking at talk radio. So we didn't really have a good picture of what that landscape even looked like. So we wanted to see, can we visualize how much of talk radio even is syndicated content? And also understand clusters of radio stations. So are there certain networks that are out there with different certain partnerships between radio stations that we have no idea about? All right, so we learned about this technology called audio fingerprinting. And the important part is that you get an audio file, and that turns into a series of hashes. And once you have the hashes, you can start comparing them. So you might be thinking, wait, this makes no sense. You are transcribing radio data. Why not just compare the words? That's a pretty common, or more common thing that you might think to do. And the answer is that we are transcribing, we are detecting duplicates within the transcripts, But there's a few caveats to that. So transcription accuracy varies with background noise, of which commercials have a good amount of, or like jingles in the background or sounds in the background. And also, it's limited to only English, and not only just English, but a very certain kind of, probably like Northeastern typical accent. So there are some places where we weren't getting as much accuracy as we would have liked, and that GoDaddy result is after our transcript duplicate detection had been applied to it. So we were hoping that audio fingerprinting might be able to complement what we already had. All right, so I'm not going to go too into this, but basically if you want to find fingerprints from an audio file, you would do some fancy FFT and spectrogram stuff, find some peaks in it. If you want to learn more about it, I suggest reading the Shazam white paper. So Shazam, for those of you that might not know, is an app that you have on your phone, and you sort of hold it up as some music is playing, and your phone will tell you what song that is. So this is the technology behind that. So really the important part is just that we get this list of hashes and at what position the hashes occur in each audio file. So that's all we need to know in the context of this talk. All right, so what existing tools were out there? There's Shazam, but we needed to find something that we could use, so like an open source library. So there's this awesome Deja Vu library written in Python, and this person who made it actually made it because he had read the Shazam white paper and thought, I think I can do this as well. So I'm going to walk through how the Deja Vu algorithm works, and this is the library that we ended up adapting. But so I'm going to go through how this one works so that I can go into how we changed it. So let's say we have a fingerprint of top 40 songs, such as these songs. And for each one, we have this list of hashes. So this is actually a MySQL database of pop songs. All right, so let's say you are at a conference, and you hear a beautiful voice coming over the loudspeaker, and you have this wave of nostalgia, and you say, I need to know what this song is. So you hold up your phone, and the song goes into your phone fingerprints it, so now we have a hash for that as well. A series of hashes for that. And then it does this comparison. So this comparison isn't trivial. It's a pretty hard comparison because it's unlikely that you held up your phone right when the song started, so it's not like you can just compare the beginning of each song. You have to compare every sequence with every other sequence in your database. So it's a little tricky, but your phone is able to do it, and it says, this is Toxic by Britney Spears. And you say, wow, I'm glad I figured that out. All right, so now I'm going to talk about our problem, because we're not looking at Britney Spears songs, unfortunately. We're looking at talk radio, which is great as well. So let's look at this pipeline. And our problem looks more like this. So you're probably thinking, what in the world is that? But instead of matching on just one song, we actually want to match on many songs. So you can think of a snippet of talk radio more as a string of possible duplicate content. So you can imagine it's more like 4 Britney songs played in a row, possibly with interruptions in the middle, like some local anchor comes and chimes his voice, and then they go back to the national content. And we want to return each of the songs that match, not just the one that matched the most. So we don't want to say, yep, that entire stream was toxic if it only matched like 25%. It's likely that different parts matched different audio content. And so talk radio is really more like a string of commercials, followed by some independent content, and then maybe clips played from other stations or jingles from their own shows played throughout the day. So that's the first problem. Second problem is that we need to know what time these duplicates occurred, because we want to be able to say from 1 minute to 2 minutes in clip A, that was the same content as from 3 minutes to 4 minutes in clip B. So don't double count those words when you're doing your trend detection. All right, and then there's a third problem, and it's a really big one, and that is the volume of our data. So we have 163 radio stations across 37 states. Ends up being 3.5 terabytes of audio ingested per month. Per day, we ingest 50,000 files, so that's a few minutes of audio per station for 24 hours. And then once we start fingerprinting it, a typical file has about 10,000 fingerprints. So, and once again, you're doing your comparison not on a one-to-one basis, but but comparing subsequences with subsequences. So it's a lot of fingerprints to compare. So the question is, how do you scale it? All right, so I'm gonna tell you. So this is our radio ingest pipeline before we did anything with fingerprinting at all. So we can think of this whole duplicate detection process and split it up into two parts. So the first part we will call fingerprinting, so the actual generation of the fingerprint tables, and the second part we'll call matching. So how do we scale up fingerprinting? And it turns out this isn't too hard. We already have, I believe, something like 40 machines that are doing our ingesting and transcription. So we just add this line and we say, hey, why don't you fingerprint it as well? And we don't really know what will happen to it yet, but just store it in S3 and we'll figure it out. So that looks something like this, where you have your audio, the name of your audio file, you have some metadata about how it was fingerprinted, and then you have your list of hashes and their positions in the songs. Or sorry, clips. They're not songs anymore. Okay, but how do you scale duplicate detection? And this is harder because you can't, it's not just a simple map, because everybody needs to know about everybody else's data. So you can't avoid comparing everybody with everybody else. Otherwise, you can't generate this nice map of talk radio as a whole. All right, so we decided we probably couldn't use MySQL anymore and decided we should go with Spark. So hold all the values in memory with Spark and see how it does. So the original code was not written in a functional way. So part of our rejiggering was that we had to rethink the process only using map and reduce functions. So I'm going to go a bit into that, but not too into that. So if you really want to go into that, I have this notebook. This is an observable notebook. I don't know if any of you have used it before, but they're really great for, we actually built this to debug some of our code, but I ended up fleshing it out into a full-on tutorial if you're interested in the actual algorithm behind it. So there are some animations and parameters you can play with. So observable uses JavaScript, so it's not the actual code, which is in Python and PySpark, but it's good for just explaining and visualizing what this algorithm looks like. All right, so let's walk through it. So you start with a list of fingerprint files. So this was output by our fingerprint process, and this is just a list of paths to the files. First thing you want to do is download them. So that's our first map. Okay, it's pretty simple. We can do that. Next, we want to group by hash value. So everybody that has the same hash value, group together. Next, we want to calculate offsets. So this is a little tricky to explain, but basically you want, so see how you have this orange content that's the same across both clips. You want to line them up. So you say like G minus G is 10, H minus H is 10, and you want to calculate those offsets, so all those 10s and that 12 and everything else. And then you want to group by those offsets. And now you can start to see how these duplicate contents start to line up. And then you want to find the time range. So let's say you have these series of hashes that match. We do a low-pass filter in order to figure out the actual time range of that duplicate content. And finally, we group again by song name, clip name. And so our output file looks something like this, where you have the name of the audio file, and then followed by a tuple of the audio file itself, what times it matched with, and then the other audio file that it matched with, and the times that it matched with on the other audio file. And that's it. So the infrastructure, so this was kind of neat because we didn't have a Spark infrastructure at all, so they told me to go do it, so that's what I did. So we used 3 technologies, Spark, obviously, EC2, and Kubernetes. So Kubernetes we were using for a lot of our orchestration already, so we thought, hey, wouldn't it be cool if we had this on-demand Spark cluster Kubernetes as well? So I'm going to walk through this. That's me. And so let's say I want a Spark cluster to run my stuff on. So I say, hey, Kubernetes, I have this Spark job, and it needs 50 CPUs. Can you help me out? And Kubernetes talks to its autoscaler. So this is something that we have configured in Kubernetes that monitors the nodes that Kubernetes is orchestrating. And it keeps track of system processes. So it can tell if a node can have more work put on it, or if we need to get more nodes from some higher source. So Kubernetes asks the autoscaler, hey, do we have 50 CPUs lying around? And the autoscaler says, no, we're a nonprofit, but I know who to ask for more. So the autoscaler goes to Amazon EC2, where we also have an autoscaling group enabled. And this autoscaling group actually bids for spot instances on Amazon EC2. So this is Amazon's way of auctioning off their extra resources. So we can make this pretty affordable. So the downside of getting this cheap price is that they can yank your spot instance away when they need to. But luckily, Spark is pretty good about being interrupted. So it would turn out to be a pretty good solution for us. So Amazon bids on these instances, and it says, hey, give me 7 machines with 8 cores. It gives that to us, and Spark says, all right, I can go do my work now. So it goes over there. It's chugging along. This process right now takes about 3 hours each day for us. So eventually the Spark job finishes, and the autoscaler says, or it notices that there are some underutilized nodes lying around. So it asks Amazon EC2 to relinquish them. So those are gone now and not eating up our bill. The autoscaler is happy. There's no jobs that require more CPU, and all the existing nodes are being used to a good capacity. All right, but let's look at this whole pipeline again, and we see that there's one super slow part of this, and that's me. So replace me with a cron job, or a Kubernetes cron job, and I can be here hanging out with all of you instead. All right, so let's look at some results. This is a visualization of radio stations in Madison, Wisconsin. So there are 4 radio stations that can be heard if you were to drive through Madison. And a line shows, or a given blue section shows content that was duplicated in any other radio station that we are ingesting. So this particular one shows for Monday, October 15th. And just looking at this, you can see right away which stations tend to air more unique content. So for example, WORT has a lot of white space where that content isn't found anywhere else in the talk radio that we are ingesting. And the neat thing about this, and you can explore it at that bit.ly link I have in the bottom, is I did this for a week of data, and you can tell how it changes per day of the week. So on weekends, WORT actually has even less blue lines, when the other ones shift as well. And then if you scroll through just the weekdays, you can see WORT consistently has that block of blue towards 10, 11 p.m. UTC. So maybe during that time they take a break and air some duplicated content. But yeah, our contact out in Madison, Wisconsin said it turns out WORT is very proud of their independent nature, and they would be very happy if they ever saw this slide. All right, so this one is an interesting one. So this is, all the nodes here are radio stations, and they are linked. So this is a force-directed graph. And they are linked if they have a certain threshold of duplicate content between them. So a certain number of minutes of duplicate content between them. And otherwise, they have a repelling force, and that's what makes them spread out. So I made this force-directed graph, and then I thought I needed some color. So I colored them completely independently of any duplicate detection results, and I was sort of shocked to see this very clear block of red, as well as this very clear block of blue-orange. So red is actually public radio, and that tends to be more the NPR stations. And blue is what's classified as news/talk. And we found that to be more of the conservative talk radio stations. So you can see this, this gap between the two. And it was sort of the first time we were seeing any of this map out in talk radio. And then on the outskirts, you can see there's one brown dot way to the left. And that is actually a college radio station, which doesn't seem to have any duplicate contents with anybody else around it. And that made sense to us and might make sense to you if you have ever heard a college radio station before. Yeah, all right, so we've been running this for, I checked my Kubernetes logs, and I haven't edited the cron job for 38 days, so it's been chugging along, and just reporting out duplicates for us. we're pretty excited to dive into a few things. One is commercial detection. So can we detect the same commercials that are airing across different stations? And then maybe we can get a sense of who is funding these stations. Are there patterns there? And also, if we remove all that syndicated content, all that national news, can we train on different accents from different parts of the country? And that could really go back and help our transcript duplicate, or transcription in general, as well as hopefully speech recognition as a whole, to not only be trained on a certain accent. All right, so I guess I'm wrapping up. All right, so relevant links. The first link is a link from a blog post from my colleagues on how they made radio searchable in the first place. So this doesn't have any audio fingerprinting, but it's a great read if you just want to learn about the ingesting and transcription process. Second, there's the Deja Vu Python library, which we couldn't have done this without. Third is a blog post on how to run your Kubernetes jobs as EC2 spot instances. And lastly, if you're nostalgic, a link to a good song. All right, that's actually all I have. I guess I think I'm done, yeah. Let's see, thank you so much for coming to my talk.
Have you thought about podcasts?
Yes, we have thought about podcasts. So we are a research group out of the MIT Media Lab, and one of the other groups has actually a podcast corpus, so we are going to try to apply our transcription to the podcast that they have as well. Yeah, so looking forward to seeing what kind of things we get out of that.
Any other questions? Or else we can break for, oh, we got one, here we go.
Do you have an understanding of your false positive rate?
Yeah, so that's the hard part. So that's something that we just started going into. For the most part, if it finds the false positive rate, at least what we have been able to tell just from listening, has been very low. If it is a false positive, then it tends to be, like they do sound very similar. Like it's maybe the opening and closing of a show, and it has like the same jingles around it. But so yeah, that's part of the reason why we made that notebook, so we could adjust the parameters and see how things change. But yeah, that's a hard problem, mostly because it involves listening to a lot of audio. But yeah, still working on that. And what we're really most interested in is the not false positive, but what we're missing. So, and we think that is quite a bit. So starting to compare that to our transcript duplicate detection and seeing what that finds versus what our audio fingerprinting finds, and trying to understand how they can complement each other is something we're actively working on. Thank you.
Final questions?
Oh, I think there's one in the back.
Oh, someone in the back? Oh, here we go.
Great talk. I have a question about how you feed the data to your model. You mentioned something about converting audio to FFT directly. Have you considered like speech to text translation and then generating encodings on top? Or
yeah, so we're sort of doing both. So we were already doing that speech to text. Since I'm sorry if I'm misunderstanding your question, but we were already doing that speech to text translation, but the speech to text is susceptible to a lot of outside factors, so we were hoping to have this around as well to complement it. Does that answer your question?
yeah, and how does the performance for the two compare?
Yeah, that's something we were just looking at this week, actually. They seem to find different things, which is interesting. Also some of the same things, but it seems like the overlap for different things is actually higher. So we're still looking into that, and it does seem like every time both find something, it is something. So we are probably undercounting all that duplicate content. And so yeah, we haven't really combined the two yet, but that's something we would like to do soon.